And I actually am feeling quite a bit better today. Yesterday I was not feeling good at all. Yesterday I was fetching a bottle of rubbing alcohol to take care of the keyboard afterwards because I felt bad for Nina having to touch it. I think I'm better today though. But I'm glad I did it because this thing's way cleaner. If you ever want to clean like finger gunk off the keyboard, 70% isopropyl actually does pretty well. I have no idea if it was disinfected, but it looks better. So anyway. Lots of people have been asking me questions about Project One. Usually what I do is just make like, the snorting noises at them until they leave. But I think I've managed to answer quite a few questions. So that's been helping. I do want to talk briefly about casting. And I'm not sure I put the little notes on there that I was going to. So I'm going to go ahead and add those. Okay. We'll actually move back to this processes notes from last time for the most part today. But reminders on this casting. By the way, the whole static casting and whatnot, I keep talking about all the stars and ampersands being put together as an incantation. That's my own term I made up. I've never seen it anywhere else. So don't go saying it at a job interview. Although I think the term's kind of funny, so maybe you should.
If they ask and you're prepared to explain it, well, maybe it'll work in your practice.
Yeah, I just want to clarify that that's something I keep making up. Okay, these static casts and casting stuff. Just kind of the reminder, the general form here. You say the type that you want to become in parentheses here. So here we have a void star px, and it's been set to something or other, and whatever it's set to, we think that it's an integer, or at least it could count as an integer. So down here, we'll go ahead and say we got an integer pointer, and then we'll make this an integer pointer, and then that becomes what it is. And at that point, we can just use it like it points to an integer. So that's a general form of casting. This is a static cast. Now in C, you don't say static cast. For comparison, just like why do I keep calling it a static cast? Let me show you dynamic cast real quick here. Okay. This is an example from CS 492 game engine design last fall. So here we have a list of objects, and these are a general type of game object. So if this block, if it's a game object that blocks things, then I happen to know, that the compiler doesn't know until this line, that it's not just a game object, it's actually the derived class block object. Maybe it's not even derived. I think it's a multiple inheritance kind of thing.
It's multiple inheritance.
Yeah, it's multiple inheritance. So I happen to know that if it's a game object in this object list and block is set to true, then it is in fact also an object of type block object. And so we can talk about it like it's a block object. So the way you explain this to the compiler is like this. We make a dynamic cast to type block object pointer, and this thing here gives us like kind of a template function. I mean, that's how the syntax works here, at least, as a template function. Actually, we're talking to the compiler here more than anything. But anyway, we make this kind of template function-like thing, and we cast W to be a block object pointer. And so now BO is it's the same thing as W, but it's of type block object star, and so we can call methods that are associated with only block object and not regular game object. That's a dynamic cast. But that's all C++ stuff, you see. We get into this whole pickle by using multiple inheritance, which is strictly a C++ thing. So the reason that we don't say static cast in C, we just go ahead and do this, is that's the only type of cast in C. So anyway, that's why we cast it there. I keep saying static cast because I'm well aware that a lot of you also use C++ and are fully aware of what a dynamic cast is, or have a vague sense that there's differences between static and dynamic casts, and now know better. Okay, declaring a function pointer type. I've seen a number of troubles with this one, and so This is the general form of these things. You have the return type, the parameter type, and you have the name of your new variable that will be created. So this line here makes a new variable. It's an awful lot like this one up here. This one makes a new variable of type int pointer. Down here, we got a new variable of type pointer that points to a function that takes a float and returns a char. So it's a more complicated type, and this it looks more complicated too. But that's how that works. So then at that point, you can just use it like a regular variable, because it is a regular variable. Okay. It just has a complicated type. Okay, using that to cast things. So I put this line right here, but it actually wrapped over because I spent a long time explaining what this parameter has to do with everything. So if you're going to do a typecast to a function pointer type, which you don't actually have to do, I've actually been encouraging people to sidestep it instead of trying to get all this stuff right at once. But if you do decide to do that, this is the way you specify this type as a typecast. So these parentheses here, we've got a typecast going on, and the type that we're casting, so just like up here, you say parentheses, your type you're going to cast to. So parentheses, there's your type you're going to cast to. You're going to cast to a function that returns a character and takes a float. So then the thing that we're going to cast is this address of a function, which is a different type, like a void star or something. And then if we wanted to call it, we could continue on here and put parentheses to actually call a function to give it parameters. And so that line illustrates what a lot of people get confused about here, which is that parentheses have quite a number of different meanings depending on the exact context. These parentheses mean to call a function. These parentheses mean to do a static cast. These parentheses are just part of the type specification. You see? So you just have to pick these things apart and see what each of the individual bits do. Okay. Maybe not fully better. The other thing that I've seen people do a couple of times here, and if you're not planning on starting until Sunday night, then maybe just remember this. So when you get a parameter that's of type void star something, and I'll call this FL, if you say this, FL at position 1, the compiler doesn't know what you mean. Here's why. Normally, if you say this, suppose you have this, int star A, okay, and you say later A at position 1. Okay, so it would have been nice if you actually populated this at some point. Maybe you did. Maybe it's populated in here, so it's an actual array. Well, when you say this, you mean the same thing as if you'd said A plus 4 bytes. So we're going to take that, and we're going to refer to the thing that it points to. But this is the important part. The reason we know that with this 1 we're adding on 4 bytes is because that's the size that an integer is. And we know A is a pointer to an integer, or an integer array, could be an integer array. And so when we say this, we know take the pointer to the beginning of the array and add 4 bytes to it. And the compiler knows that. You don't need to say like 1 times the size of an integer or anything like that. If you say this, well, FL is a memory address, but we don't know what type it points to because we didn't say. We said void instead. So the compiler doesn't actually know what the offset associated with a 1 is. Sometimes people have been tempted to fix this by putting an ampersand here. I've seen this a fair number of times. And so this makes the compiler error go away. The reason is it changes types. And so if you say the address of the F1, the type of this whole thing here is a void double star. The reason it's a double star is it was a void star, and we're looking at the address of it. But the problem is, at least as far as it pertains to project 1, if you do this for your parameter, what the void star is the address of is the parameter to your function. And so that's the address that it'll try to add 1 to, which is not going to be the address of any valid function. And so then it starts running code that it doesn't even know where the code is. So if you run this in a debugger, it gives you an error, like usually an illegal instruction or something similar. I've seen a few varieties on this. But either way, is an error in somewhere it doesn't know about. So if you do backtrace, I've seen a few variations of this. Sometimes I've seen like a whole bunch of apparent stack frames. Sometimes there's like only one. But regardless, it doesn't really know what function it's running. And so it'll show great confusion about what it is trying to do. And the reason is, it's taken the parameter f1, gone one address past it where there's nothing in particular, assumed that that's the address of a function, gone to whatever that happens to be the address of, and then tried to run it like it was a function. So the usual way to straighten it out, you got to cast f1 as a void double star first, and then it fixes it. So that takes care of that. Okay. Anyway, so that's the major things I've seen. I haven't seen a whole lot of other things. If you haven't done the sorted copy yet, remember to actually keep allocated space. And don't try to allocate it in a stack frame or something bad will happen. Remember how bitwise and works. Good. Okay, and I've seen a lot of these been now, so it's just going okay. It's not going to be like a project to do. Okay, so processes. Actually finishing the part of this that we didn't quite get to last time. And yeah, we did the proc entry. Well, we haven't talked about processes and threads and stuff like that. Okay, so computers have always supported multiple processes. So if we go on this computer and read PSAXU, you know this is a list of processes it's running. So for example, there's this process called rat poison right here. Right around the middle. Now, I happen to know that rat poison is my window manager that is taking care of drawing this stuff. Rat poison is a very minimal window manager. It doesn't add a whole lot. There's no X in the corner of the screen. There's no taskbar. I don't like all that stuff because it wastes screen space. And on a projector here, you'd think on a projector we'd have a glut of screen space, right? But I have to run a big font size so everybody can actually see it in the back. So I actually have very little space here. Really don't want to waste it. And even so, screens are expensive. You know, you buy a more expensive screen, it costs, it's bigger and costs more. And projectors aren't cheap either. Well, that one might be, but yeah, in general, no. No, seriously, you get a projector like that for $400. If you find a used one, you know, like more like that, it's probably $100 on eBay, and you can get remanufactured bulbs for about 50 or 60 or something like that.
But the bulbs generally are way more expensive.
If you buy a brand new one, NEC, it won't be, but if you get a cheap remanufactured one, it's kind of plus.
Oh, you may even garage sales.
That's got a cheap remanufactured one in there. I told you guys about the most idiotic thing I ever did regarding multimedia equipment in this room, was just fix that thing. Instead of just having the division buy us a $1,000 projector with a bulb film. Anyway.
Yeah, and now they know you can fix it, so they're like, we ain't buying it.
Oh yeah, we're stuck with that thing until I retire.
Or until it actually has a catastrophic failure.
So, what this is leading up to then? So, rat poison, right?
Yeah.
Kill all rat poison. Sure, don't even need to pseudo it, I don't think. Okay, so they got killed, and it gave me this little note here. But then the funny thing is, it actually goes back. Okay, so if you look at this, rat poison is actually in a different spot on our list. Let's do this and grep for it. Okay, so you can see there's actually a number of things related to it. Typically, when you have a windowing system, it ends up with a few processes for various reasons. We won't go deeply into window manager design. And of course, the bottom was just my search. You can see grep color equals auto rat poison. So it's going there. And it's only been running there since 10:45. Because when I killed it, it got restarted. But if you look up here, this 1031 process, when I started this computer up here, we appeared to debus launch something, exit with session, whatever. Anyway, it's process 2748. 2748. Hey, there we go. We just killed the window manager. Completely gone? Oh, something came back. Well, look at that. Something else restarted it. What could that be? So, LightDM is our display manager. And so LightDM takes care of making sure that, first of all, the display server is actually running, And secondly, that there's an actual window manager running on it so that windows can be managed. And so when we killed the window manager, it went and restarted it for us. And you can see it's running with root privilege, not necessarily me privilege. So what happens if we kill that one?
Ooh, I want a password.
Okay. Now there's nothing on the screen. Uh-oh. It's back. Again. I ended up logged out this time. Okay. Well, there's a service command on here, which can show you all your services. If we look at all services, we can see that the Light DM, the display manager, is actually a service on the machine that's managed by the service system, which gave us a new one when we kill it. Okay, now we have told the service system that it should get rid of Light DM and not restart it. So now the screen is black. And pushing buttons is no longer helping us. So we tried very hard to get ourselves into a problem. But I'm going to hold down the Control and the Alt keys and press F1. And so now in the text that you can't read, it says MLH310-0 login. I'm at a virtual terminal for the system. If I go ahead and log in as me, I should be able to log in. I think I just typed that wrong. Oh, I can see actually what I did wrong. Okay, so now I'm logged in. In a text that you can't see, it has the regular prompt. Now if I start something like Google Chrome, it tells me in text that you can't see, if GTK error cannot open display, because we have actually managed to stop it. Let's go ahead and restart it and get on with things. Sudo service light dm ght dm start. And that will restart the display manager, which will come back up here in a moment, and allow login. Okay, so we are back. So that's processes on the system. Just a brief example of some various system processes and why do you, when you type ESAXU, get this crazy list here. If we clear that out and run that in the word count, you can see we've got 214 lines. And there is a header on that right up there that says what each of the columns mean. So there's actually only 213 processes running on the system, not 214. But either way, that's kind of examples of how we get to this high number, 213 processes on this machine that we really just started. Just booted it up and it had all this stuff running on it. It used to be a common exercise back in, especially like Windows 95, 98 era. All the nerds did this. You'd look at your task manager and scrutinize all the processes and then stop the ones from starting that you didn't need. And it was very fruitful on Windows 95 and 98. Like you'd find a number of processes where you're like, this thing is the AOL process that came with the installation on this computer. So you just get rid of it and it boots up faster and you've got more memory for everything else and everything's better. There's also a good Thanksgiving trick. Like if you went and visited a relative for Thanksgiving and you're like, man, my computer's slow. And you go through and get rid of all unnecessary processes and you're like, wow, that was like magic. It works great. And gorillas don't appear in the corner anymore. You're like, yeah, that's because you clicked on the thing that makes gorillas appear on the internet and installed it. And now it's spending 5 minutes every boot up trying to connect to the gorilla server to figure out what the reward of the day was.
And then you tell your family, thanks for choosing Seth's computers. That'll be $49.95.
A lot of times you can do it every single Thanksgiving with the same result. Anyway, so you got all these things that appear, and so you can. They've all got rules, and if you go, if you're ever curious what one does, just stop it and see what quits working. There's no real harm in it. Typically, if you reboot your machine, everything's fine.
I did that on a Windows machine. I just went through and stopped everything that I could stop until eventually I got down to just Explorer left and a couple of other vital things, and then you stop Explorer and everything goes black.
Yeah, you can't stop that one.
Well, back in the day,
But,
when we had less system resources, it was fruitful to just
Oh, yeah.
bare bones it, so that way,
Mhm.
whatever you're doing,
Did it
whatever
all the
game you're
time.
in, yeah, kept it clean.
Okay, so that's the processes that occur. Now, the operating system, people kind of use this word in two different ways. If you say operating system in a systems programming sense, you typically mean the kernel. If you say operating system in a more general sense, you mean the kernel and all of the things that came on the operating install CD, excluding the things that came on the install CD that you don't want, which is a little bit more complicated and nebulous definition. But if you install, for example, let's talk about Apple briefly. I never talk about Apple, so I don't know anything about Apple. So let's talk about them anyway. When you install Mac OS X, you actually install a certified Unix system that's actually fairly open, using used to call it a Darwin kernel, but they've modified it over the years. I'm not sure if they still do. Anyway, so you install a certified Unix with a command line interface and everything like that. And you install a highly proprietary graphical system that's provided by Apple that you cannot see the inside of. So once you've got these two things, along with some other things that come with it, like the Safari browser and whatnot, you'd say, I have now installed the operating system, and then you can use the computer. There's a legal case actually about maybe 15 years ago relating to Microsoft and this kind of thing, and whether or not Internet Explorer was a vital operating system component. It was an anti-competitive case in the Netscape Navigator era because Microsoft bundled Internet Explorer. Most people, when they install it, you'd have Internet Explorer, so what do you need to go download Netscape Navigator for? They do kind of the same thing, so they use Internet Explorer. And Microsoft argued that Internet Explorer is a vital system component and cannot be removed. And if you wanted to verify that, you just go on Windows 98 and stop the Explorer process, and your system would quit working right. I don't know if they engineered that to bolster their argument or not, but anyway, that was the argument that was given. Okay, so anyway, when you have a complete operating system, everything ready to use, you have both the kernel and all this other stuff that came with it, which is where all these processes come from. The kernel doesn't have any process entries in that list. Doesn't work that way. So you got those. Now we've got another concept here called threads. And the definition of threads and processes is a little bit nebulous, but the usual agreed upon factor, based on the Unix type systems, is if you run something like PSAXU, what you're going to get is a list of processes, and any of those processes may have more than one thread. So if you've got a process with 8 threads, you get 1 entry here. And so if you run pop here and see all of your processes, most of them aren't using very much CPU right now. Let's go ahead and make one use some CPU. We'll generate ourselves an SSH key that we don't need. Okay, so we should see a process pop up there. There it is.
Whoa.
63%, 100%. There we go.
Wow, it actually maxed out the CPU
It
for
did.
a moment.
It was using 100% CPU for a moment on 1 core. Now, the percents in this graph are per core. And so since it went to 100.0 and no higher, it probably was just using 1 core. If you have a process that has 8, since it had 8 threads, then you could actually get it to say 800% up there in the CPU utilization. So that's the difference with the threads. Now, that's the difference in how they display. If we talk about how they work internally, so processes typically don't share memory. When you start running a program, you don't expect you're going to be sharing memory with the web browser, for example. I'm sure you're both competing for the system memory, but you wouldn't expect that you go to access some array and, oh, wait a minute, the web browser just changed the contents of this thing,
They get their own little allocated chunk.
Right. So each process is presented a clean memory space. And so if you use a memory address for your process, you're the process that uses it. There's mechanisms to share between processes, but in general, clean space. Threads, on the other hand, have a common space between them. And so this can actually make it much easier to do a multi-threaded computation using a bunch of threads instead of a bunch of processes. Since you can just have this common memory space and each of them can collaboratively change it. So that's the difference there. Okay, there's for a while been a lightweight thread concept. It's kind of going away. The lightweight thread idea was that so sometimes, like with an internet server, with a server of some sort, say uses TCP, transmission control protocol, and so it establishes a session with a client. You might have to spawn a thread to talk to a particular client. And so if you've got 10 clients and are hardly ever saying anything, but you've got a thread for each of them, it's handy to have a lightweight thread mechanism that doesn't use a lot of resources for that thread, even if the threads can't even be migrated to different cores. But these days, most of the threading systems do expect that you can move things to a separate core. Okay, so let's do each of these and see what happens. Okay, what was that? Let's actually go with P threads first, because this will be fast and easy. Okay, go to the examples area. Maybe this time. Okay, I think I botched that again. I need to stop trying. You know, I've talked about this before. I always try to make passwords faster than everything else, and it just doesn't work. Okay, there we go. So, thread.c. Okay, so I'll make a program that does some stuff in threads. We'll calculate Fibonacci numbers or something. Yeah, exciting, right? Okay, so I suppose we got some program main. Okay, and we want to run something in a separate thread. So int fib.calc. Okay, so this figures out Fibonacci numbers. Let's actually go for a long int, long unsigned int. Okay. So we'll do the really slow algorithm because I want this to actually take a while and present a load to the CPU. Okay, so if n is greater than, I guess about 2, turn fib.calc of n minus 1 plus fib.calc of n minus 2. Okay, that generally does. And then otherwise, we're going to return 1. Because Fibonacci sequence, first two numbers are entered are 1. And so if it's not greater than 2, so the Fibonacci, the number 1 and number 2 in the sequence would stay a 1. And so that should give us the right kind of thing. Okay, so if we wanted to run this down here, we could just say fib.calc of, say, 35. And yeah, no, we'll run it. BCT thread.c. Should block out the bottom half here. Okay. So, it does it. Doesn't turn out the result. That's fine. Okay. So, doing this in a separate thread. So pthread creates new threads using the pthreads library. It takes a few parameters. So the first one is a thread object, which has to be a pthread t. And you can see the type there. It's got to be a pointer to a pthread t. Okay, no problem. We can do that. So that was the type. And we'll call it our thread. So we get the address of our thread. Okay, next one. So it calls pthread attr type pointer. Attr. So this one can actually be 0 if you want. It says down here the attr argument points to a pthread attr t structure whose contents are used at thread creation time to determine attributes for the new thread. This structure is initialized using pthread attr init and related functions. If attr is null, then the thread is created with the default attributes. That sounds good.
Question is, what are the default attributes?
They're fine. Whatever they are. Okay, so then we got a void star returning start routine that takes a void star. So this is a function pointer right here. Now it doesn't match the type of our function. Our function returns a long unsigned int, which oddly enough is actually the same as a void star. Void star is also an unsigned 64-bit value. But it's of course declared different. And it takes as a parameter a void star, 64-bit unsigned integer. We're taking an int. But we can adapt to this pretty easy. Okay, so we'll just say that we return a void star. That'll throw a warning. And we'll say this is a void star. We're passing a bigger value for n since we take a 64-bit now. And it's going to throw a couple of warnings. We'll fix those and make them go away. Okay, so that's now the correct type. And then the next thing is a void star, our argument. So we get, again, an unsigned 64-bit integer, which actually is the type that we just said we take. So we'll give that 35. Okay, again, there may be a warning. So instead of running it down here, we won't do that. We run it with this pthread create. So now we need to wait till it's finished. So the way we do that is with pthread join. Okay, so pthread join takes a thread up there, and it can have this double star ret val. And we do want ret val actually, because that's how we get back the value that our thread function returned. So if ret value is not null, so you can just make it null if you want to ignore it, then pthread join copies the exit status of the target thread and the location pointed to by ret val. Okay. So if okay, so that should give us hopefully what we're after. Okay. Now I want to say void double star. I can do that. Okay. So let's say we have a void star ret val, and so if we pass the address of that, then it's a void double star. Okay. The reason for the double star here, it expects this to be a type void star. However, it's going to change it for us. So if it changes it, it needs to know where it's located. So that's why it wants the address of a void star, like we said there. The address of our void star is really a clearer way to state it than a void double star. But of course, in the function parameters, it shows up as void double star, because that's what it is, the address of a generic address. Okay, so let's print out what we got back. Was percent sign, the LD. We'll do a long one. We'll just print out in base 10. That's what that does. Okay. Now, we should verify that it's correct, too. Okay, we'll do fib calc of 35, which is just the normal way to call that function in the main thread. Okay, so let's see what happens with this thing. Yeah, oh, actually, let me read this out real quick. Okay, so, oh, that's actually a little bit different. We'll have to take care of some of these things first before we get to our linker error. Okay, so first one here, comparison between pointer and integer. Okay, so what we have there is n, that's a void star, a memory address. That is an integer. We can cast it as an int, but it's actually a 64-bit value. So maybe a long int would be a better choice here. And it's actually unsigned. So if we want to be really particular about it, we could do that. Okay, so that one went away. Next one, error. Invalid operands to binary plus. We have void star and void star. Okay, so you see we're going to end up running into this thing every time we say n, which could get tedious. So here's one thing we can do about it. We know n is an unsigned long int. So we'll just say, call this one arg, and we'll say that. As far as whether we cast it or not. So we could cast it here for the static cast. We probably don't need to. That will do it for us. So where was our first one? Oh, right there. Yeah, well, I guess it would like it to cast. That's fine. Okay. So now we got a warning. Passing argument 1 fibcalc makes a pointer from an integer without a cast. So n is an unsigned long int now. 1 is a regular int. And so when we do this arithmetic, we're left with an integer. And that's actually fine. I mean, that's pretty much what this takes, right? Yeah.
Is U in 64 or concede if you have to really tell them it's a long int?
I think you can say UN64. Okay, so we'll cast it. Okay, now we've got void stars here. That's because that's what fibcalc returns. Returns a value type void star. There we go. Okay, now what is making a pointer from an integer without a cast? Well, that is, of course, oh, the return itself. Right. So like here, that would make that go away, right?
Oh, Lord. So much
Okay.
casting.
So then
No
down
kidding.
here in main, pthread create, again, this 35 is an integer, and it expects a void star. But of course, that's fine. Okay. Now this one, implicit declaration of printf. Well, we know why that one happened. Okay. Pointer from integer without a cast again. Yeah, fibcalc returns a void star. And, oh, no, it's right here, this one. Okay, good. We're down to linker errors now. So the linker errors, we've got undefined reference to pthread create and pthread join. And looking at this at first glance, if you're thinking about like a compiler error, you might say, wait a minute, I totally said pthread.h here. Yeah, we did. That's why we didn't get a compiler error. We got a linker error. The linker error means that, sure, it compiled fine. That's why we're talking about this object here that we built. But we can't figure out what was actually meant by this pthread create that compiled okay because it was in a header file. That's because it doesn't automatically make the pthread library.
So another
There we go. Now we are set. So it appears to work. That's apparently the 35th Fibonacci number. Didn't know that. Let's do this, make this hard enough that it actually slows down the system a little bit. Instead of 35, let's go for 40.
I'm surprised that you had to do that switch or the argument on TCC when you've included pthread in the header.
Well, yeah, but it doesn't automatically go find the library for pthread.
Well, then what's the point of the include?
Yeah, we'll have a compiler error if we take out the include. So if we go take out this one, it'll be somewhat earlier. Okay, so it gave us these implicit declaration, so we didn't use the header file there. It didn't actually give us a suggestion about where it is. And then here, this pthread t, it's unknown type because it's defined in a header file for it.
I'm just surprised that you had to add the minus pthread argument to TCC.
Then it doesn't go look and see if there's this include, and if that include happens to be there, then it adds it itself. Yeah, it could have been automated, but okay. So that was 40. Let's go. That was 40. Excuse me. Let's go for 45. Unfortunately, it's running pretty fast.
No, software's a buff computer.
Yeah, but you can always just give it a higher number.
Yeah.
Okay. So now it takes a while for each of these. So let's
1.1 trillion.
get rid of that one and get a second one of these things on here. Actually, I wanted that. Yeah. Okay. So when we run this, we'll still only see 100%. The reason is we did one of our calculations and then we did the other. And so we get 100% running on a thread, then we get 100% running in the main thread, and then it's done. So let's edit our program lightly. And it says pthread join is where we wait for it to be finished. And we'll take this printf and we'll move it up here. That's the one we're expecting. And we'll say expecting value, whatever it is. And so then we'll start the thread. Then we'll start calculating the one that we're going to compare it to see if our thread got the right answer. And then we'll wait until it's done. And once it's done, we'll print out what the thread returned. Now, it might be done before we hit pthread join, because we're going to start a thread running, then we're going to do the same thing. So this is going to take just as long as it takes our thread to run. And so it might be that the thread actually finishes before we get here. But it's fine. This just enforces that we have to have, the thread has to be finished before we get to go on. Okay. There you go. 200% CPU usage. Because we were actually using 2 separate cores. So that's how you use the threads. If we went ahead and did this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. We don't bother to wait for the rest of them to join. So we try it. Then we should be able to get a higher number on there. Hey, there we go.
2176. 2498.
Yeah. So that's how you use all of my software. Is you start a whole bunch of threads on it, and then you can do that. Okay. In order to leave the demo in a more like normal spot, I'll go ahead and remove this. Okay. So that's the threads and how to do stuff with threads. So that's really pretty easy. It doesn't start a new process. You notice we just had our one entry in the process table. It just gave us a higher percent. So we just used it for some computation of something, something pretty useful, really. Okay, so that's it. Now the other things on there won't make sense necessarily until we talk about fork. So let's talk about fork. Okay. I talked about that a little bit this time in Linux, but it's not always really a major topic in Linux because people don't really have to know how C programming works in Linux class. I kind of wish everybody did, and then it could move to like Unix programming instead of 228, it would be like 328. We learn a little bit more stuff in it. And I sort of run out of what to say about the command line halfway through that course. Okay, anyway, so fork exec. Okay, so fork exec works quite differently. So I have a program here. So fork system call. This is what fork does. You have to include unit std.h, and so fork creates a new process by duplicating the calling process. So it works a lot like a worm or something, where it's like a reproduction. So right. So the fork. Okay. So let's go ahead and run fork here. Right here. And it'll return something, a PIDT. Result equals fork. Okay, let's go ahead and include the right one for it. I sort of figure out which one it is. Unit STD. Okay, and we'll go ahead and print out this result. Now, the result is of type PIDT, process ID type. And I think that's just a 32-bit integer. So I think it would be %ID for printf. Okay, so there we go. They'll take our PIDT result and print it out for us. Okay, so let's cut the program here. So you can see from this program, we ran it, and we declare this local variable, PIDT, and then we call this function fork, and then this line actually printed out twice with different results. One time the result was 30,038, and the other time the result was 0. And the program looks pretty goofy when you look at it like that. Like, wait a minute, this line ran twice? Yeah, it ran twice, that's what it did. Yeah, I realize that's probably what everybody's wondering here. is if I were to take these two lines and duplicate them, would we actually get more than that results?
Yeah, I think so.
Yeah, we do. We get 6. Why 6? Well, let's talk about why 6. Okay, so we got 30,086, we got 30,087, we got 0, we got 30,088, we got 0, we got 0. Oh, let's run it again, too. And let's run it once more. Okay, so you can see that the results weren't exactly the same every time. In this case, they were all very nicely interleaved. We had like the 30,000 something number and then 0, 30,000 something, 0, 30,000 something, 0. In this case, they were again not interleaved. They were in different order, like that. Take this thing back to the original one right here, and I'll finally explain what's going on. Okay. Okay. So what's happening is when we hit this fork, it's taking a process and splitting it into 2 processes. Both of the processes are the same, but the result returned from fork is different, so you can actually tell them apart when you're in each of them. Let's go ahead and count our Fibonacci. Oh, just go ahead and redo it. Okay. Let's go ahead and do the Fibonacci thing right here, too. We'll say up here, fib and n. Okay, we already did this. Yeah, and 2. Okay, I thought about copying over. We had to remove all the casting. Okay, so let's calculate the Fibonacci number for 45. Okay, that's going to be what right last time. And then I'm going to go ahead and take out that frame and put them like this again and rerun top down there so you can see it's running on the system memory. Well, you can time anyway. Okay, so now what we've got is 2 processes. They're both named A.out, and they're both burning, well, they were burning, 100% CPU for a moment. So, actually, we can go even further than 45, so I can talk about this for a minute. Okay, so we run A.out here, 2 processes. If you look at the process ID here, see what 3231? 3231. That's what that return value is. It's a process ID, like it shows up in this table. These are both individually using 100% CPU. So we've got 2 separate processes that are now just doing the same thing. And they have different PIDs. Like, if we look at this again, let's run this one more. Okay, so you got one of them is 3253, the other is 3254. So they're actually consecutive. They don't have to be consecutive, that's not guaranteed, but our program forks almost immediately. So since these process IDs are just kind of allocated when a new process is started, they happen quickly enough that they happen to be consecutive ones. Yeah, anyway, off they go together doing their thing. So fork actually duplicates your program. So suppose we wanted them to do different things. If result, and so now we have a choice. Okay, if result, then we're actually called the parent process. Otherwise, we're the child. Okay, so we'll say that children don't have to do as much work. We'll go for 45 there. Okay, and we'll go ahead and print out the results of this. LD. Okay. In order to save some typing, I'm actually going to nab that line, put it right down here, and then just change this one word. Okay, that's 45. Okay, so let's run this thing. So then they are both working together. Both hit 100%. Child is done. And then eventually, the parent will finish, having had a much larger number to calculate. So you can separate by looking at that. Now, so the parent is returned the process ID of the child. The child does not actually get handed a process ID at all. They get a 0 to indicate that they are, in fact, the child process. So now the parent process has finished and all done. Okay, so that's fork and exec and the fork exec model. Now, after you've run fork, you essentially have two separate copies of your program running. And so communication between them actually gets to be difficult in some ways. You have to use some sort of mechanism for it. You can't just keep going as though they're the same program. There's mechanisms for it, such as pipes. You can set up a pipe, and it works a lot like a network socket. If you were a networks last fall, you just put stuff in one end of the pipe, it comes out the other end of the pipe, and you can communicate between them. Or you can establish a common file that both processes have open, or other various things. There's never been a super standard unified way among Unixes to have a shared memory area, but most of them do have a way to have a shared memory area. So you can do that. You get a few ways to communicate there. Okay, so that's how it works. So the parent in this case takes a lot longer to finish than the child. So let's go ahead and take a look at this. Okay. So they're both named A.out. And so if we look at A.out here, here's everything that's got A.out in it. It looks like Alex is with us in a remote sense, running something called A.out on Isoptra. I'm not very surprised. Okay. So we'll go ahead and run it, and then we'll look at this. So they're both running. That's what R+ means. Oh, the child is done. So the parent's still running. The child is now defunct, and they're in status Z. You can see they're still in status Z down here. And once the parent finishes, then they'll both go away. So the child's finished, but they've still got an entry in the process table, even though they're done with their calculation at the end of the program. So they run it once more at the end, and they're all gone. So status is on there. S means stopped. And so my grep process there is probably just currently waiting for PS to finish and hand it some input. And so it's very temporarily stopped. Alex's processes apparently don't need the CPU right now, whatever they're doing. So they are also stopped. The A.out was, of course, running, and the child has turned into a zombie.
Now the parent must kill the zombie child.
Well, you wait on it. Okay.
You just wait
So
for the
here's the
zombie
status
to die.
codes all listed for you. So there's a few that you didn't see on here, but we saw R for running. We saw the ones that were stopped and in interruptible sleep, and we saw the Z defunct zombie process. Terminated but not reached by its parent. So that's what status the child ended up in there. We're waiting for the parent to finish. Okay, now you know. Oh, and then there's some other characters that indicate certain things. Is it a session leader? Is it multi-threaded? Is it in a program? Is it that anyway. Okay, so that's zombie processes. Okay, so if the parent just kind of like hangs out and doesn't do anything, then the child just sort of stays as a zombie. So suppose after the parent's done with this, the parent decides to calculate the another Fibonacci number. So we'll say printf starting even harder calculation. Okay, and we'll go ahead and calculate the 49th Fibonacci number. Okay, but suppose we don't want to leave zombies about for all this time. Sometimes you don't want to leave a zombie around. Some people just don't think that they're very clean to have on your system. So we have to wait on it. So that's not the right way. Okay, so wait. So wait waits for a process to change state. And so when we call wait there, we can give it a W status. We don't actually have to, but we can give it a W status. We can wait for a particular PID if we want to. If we just use the regular wait as a parent, it'll wait for whichever child happens to die first. This is a status that most parents wait in. Very few of them wait for a particular child to die before the others. So then we have, the variations here, but basically, we want weight up there. Okay, and so for the parameter on weight, this W status can actually be set to 0 if we want to, if we don't care about the status, I think. We'll see what happens there. Okay, so let's go ahead and call weight here. Okay. We'll do this first. Let's go ahead and make that one. Okay, implicit declaration of weight. That's for weight. It looks like it's we need sys types and sys weight. Sure, do that. Okay, there we go. Oh, I didn't want that. I wanted the PS one. Sorry, I botched the whole thing. Let's do this again. Okay, so at first you can see there's not really anything with p.out, so we'll run it. You can see they're both working together here. Both are running. Okay, so now the child is a zombie. Well, the parent is busy calculating the 48th Fibonacci number, which takes somewhat longer. So once the parent finishes with that, hit enter over here, and we'll see the result of weight. And so with weight, you can see the child is now gone. They're not sitting around defunct anymore in the zombie status. And so then once the parent finally finishes the rest of the way, then the last A.out will go away, and that'll be that. It might take a little while since we're doing an even higher Fibonacci number. Okay, so that's statuses and whatnot. So now you understand what happens if the child dies first. Now, the other possibility is the parent dies first. And we can make that happen easy enough if we want to. Okay, there we go. There's the last status. See, all done. Okay. We put this in the head. We need to see the parents of processes. Okay, so we can see process of the specific parent ID. Set up some of that. Processes marked defunct or dead processes, so-called zombies, are named because the parent is not destroyed properly. They'll be destroyed by init if the parent process exits. Okay, P is parent process ID. Okay, so let's do PS APXU. Okay, that's not quite what we wanted. I want PS to print out the parent. I should have looked at how to do this ahead of time. What's going to happen is that it's going to get adopted by the init process, and so the parent is actually going to change. And so that's why I was hoping that we could have it actually output the parent. We've been using the BSD syntax here, so we've been doing PSAXU in order to see every process on the system, including information about users and that kind of thing. So there's a list of format control, modifiers, thread display, other information, process state codes, obsolete sort keys, format descriptors. PS is a complicated command here.
Obviously.
A little bit.
Personality. Okay. Well, maybe I want to demonstrate it on there. I'll look it up sometime and read that man page during lunch or something. That's what I should have done. I hardly ever use that particular feature on PS, and so I don't really remember it off the top of my head. Okay. What's that show me? No. Okay. I actually kind of thought it was on PSAXU, but I can see that it's actually fairly clearly not on PSAXU. So anyway, there's an init process, PID0, that adopts anything that's parent has died. I noticed in the, I read you a brief thing from the man page about if you have a zombie and the parent dies, then the zombie is destroyed by init. Basically, init calls wait on it and gets rid of it. And so that's what happens. They get adopted. So you don't have to worry about the orphan children or the orphan zombies. Okay. We used fork and exec. We haven't used exec CDP. Let's use exec CDP real quick. Okay. So we'll make something that starts the browser. Just gonna go. Okay. So we're gonna include using SGE.h because that has fork and a lot of the others. Let me show you the exec.ve family of functions. So exec.ve executes a program. You get a file name, and it runs it given a particular argv and a particular environment pointer. So, with main, you take argv as a parameter. If you're going to use exec.ve in order to start a program, you actually construct an argv array and hand it to the program as the argument for main. Okay, now there's a whole family of exec.ve functions. And so here's another one, exec.l. So, hey, you got this shows a lot of them. One of the neat things about exec.l is you actually give it a path that will be evaluated on the system path. So you don't actually need a file for your program to run. You can run kind of more of a system command that the system can find. And a number of these take a path. So like exec.v down here is a pretty easy one. You give it an argv you've constructed, and you give it a path, and it runs it. So let's go ahead and use exec.v. I think that'll be a pretty good one here. Okay. So start browser.c. So what I want to say is something like exec.v, if I can type this right, and then give it a program to run, say Google Chrome. Oh, this is not going to work on a software because it doesn't have web browser on it. And then an argv. So I need to make an argv. Okay, so let's say this is an array of character pointers. Argv. Okay. Let's make a static array of 3 character pointers. I'll say argv at position 0 equals Google Chrome. That's the name of the program we start. You know how the first thing you see in argv is the name of the program that you are? That's what goes there. Then the next one is the site that you want to open on Google Chrome. And so we'll just say software.lcsc.edu, because where else would you want to go? And then the last one, we'll set to 0. And that indicates there's nothing more in argv. That's the end of it. Okay. So there we go. Now we'll go ahead and print out something. We'll say printf about to start Chrome. Okay, then we'll print out something else here. Now we're done. Okay, ready? Here we go. So, pointer makes an integer from pointer without a cast. Why are we doing that? Oh, we made an array of characters. We didn't make an array of characters. Okay, implicit declaration of printf, sure. Okay, it built. Now, I mentioned that if we run it on here, we're going to get some problem. I'm about to start Chrome. Now we're done. No sign of Chrome. command not found. So that's what happened. Returned an error. So let's grab it on this computer. Look for these samples, and I'll copy them all. Actually, what SSH test. Is that a directory called examples? Hold on a minute. Yeah, apparently. Okay. Oh, we still got it.
No Chrome. Oh, wait, there it
That
is.
works. Interesting. That didn't work for what do I call it? Start browser. Okay, so we got some kind of error here from exec.de, and so we'll go ahead and print it. Okay. Oh, maybe it's the error. Better. Okay, error. No such file or directory. I used the wrong exec.de. Hold on a minute. Because if we put user bin Google Chrome, which is where it is, and it fixes it, then we will know that okay, that comes up. Cool. Now, Chrome itself knows that it's being started, and that it in fact already has a session, and so I added a tab to its existing session. Clever like that.
Yeah, that's intuitive.
Yeah, that's what it always does. In fact, it even told us that. Create a new window in existing browser session. Now, you notice something missing?
The done.
Yeah, it never printed out, right? Okay, so here is why it never printed out. What do we use? Exec.v? Okay, return value. The exec functions return only if an error has occurred. So if they work, they do not return.
Interesting.
So here's why they don't return. What's happened is the exec process, it takes your existing process, the exec function, it takes your process that you're currently running and turns it into a new process using the same process ID. So you don't get to keep your current process. So the usual way this is made to work is with a fork. So if we take this start browser thing, say about start Chrome, okay, fork. So we might be the parent or we not, or we might not. We'll say PID type PID equals fork, and then we'll say PID parent. Then we can do what we want. Okay. So let's just keep going through. In order to avoid scrolling off into oblivion. I think sleep is in time, if I remember right. Okay. Then if we're the child, we'll leave the error handling of the child. It will only print out this error if something actually goes wrong. If nothing goes wrong, exec doesn't return, and we won't see the error message. Okay. And I'll just clear it back to the top. Okay, so there we are. We opened up Google Chrome, which is what we intended to do, and the parent is still there. And will stay there until we control-C it. Okay. So this is the fork exec model used to start other processes. And this is the same kind of thing that a shell, for example, will do. When you're in a shell and you run a command, it will fork and figure out what to do with your command. Your command might have things that need to be expanded, like names of variables or backticks or all that other stuff. Figure out what to do all that stuff, and then exec the command you intended to run in a child process. And the parent process for the shell keeps running, and in fact, it even keeps listening. So if, for example, we were to run this thing, and so here goes. Okay, the browser tab's open. Close it. and this thing's running, I'm gonna hit Control Z. So the parent process from the shell was listening and heard the Control Z and stopped its child process, the parent process from Star Browser, and it's currently stopped. Yeah.
So here's a question. In a weird sense, can grandparents kill grandchildren? So if we had a parent process and then a child process, and then that child process makes another child process, if the parent and the first parent process finishes, okay, there's weird things going on. Do you get what I'm trying to say?
Yes. And what
Okay.
you're asking about is the signal interface,
Okay.
which I would talk about today if we had another half hour,
Okay.
but it's going to have to be Tuesday. But basically, the answer is yes, they can send a signal.
Okay.
If you know the PID of the process that you would like to kill, you can send them a signal that politely asks them to die. They can either respect it or not respect it. If you have the appropriate permissions, like if it's running in the same user level, you can tell the operating system that the operating system needs to kill it, and that it's not playing ball and dying on its own. And the operating system can do that. But of course, if the process is owned by somebody else, like a different user on the system or root or something like that, then the operating system won't respect your request to kill it. Yeah. Okay, so this thing stopped. We want to bring it back. FG brings it back, and it's still running. Control C will actually do away with it. Okay. So that's kind of the introduction to processes. And so yeah, next time signals and how to send signals from one thing to the next, how to handle signals on the inside, how to make a process that denies all polite requests that it ought to die. So it'll be great fun. You had a question?
Are you familiar with NoHub?
NoHub?
Yeah.
Oh,
Like
I do know what you mean.
is that like a running on a background thread or?
I never use that. I always use Screen for that.
Okay.
Yeah. Yeah. We can look into that next time too if you want to add that on there. Any questions?
Yes.
Okay, well, I'll see you all next time.